Okay, if there are no questions, let's get started. So today we're going to do section 3.5. It's about something called change of basis. Okay, really the way to think about it is the change of coordinate systems. Okay, so remember last time we said that we made this thing called a basis, right? Somebody tell me what a basis is. What's a basis? If you were here last time and awake, then you should know what a basis is. Okay, choose somebody random. Dan?
It's a set of vectors such that their multiples make up the entire span?
You're garbling a little bit, but you're not far off. Keep on going. And one more thing.
Closed under addition and multiplication.
Yeah, now you're getting farther.
Sorry.
It's okay. Linearly independent. Linearly independent. Okay. So remember what a basis is, right? The basis of a vector space, right? It's a set of vectors, right? A set of vectors, right? It's some set of vectors such that the span of the vectors is all of V. Okay, so they're a spanning set, right? Everybody in the vector space is realizable as linear combinations of these guys. Okay, everybody in the space can be realized. Each vector in the space is a linear combination of these guys, and two, they're linearly independent. Right? Okay. And remember what's good about linear independence? That everybody who is expressible as a linear combination is expressible uniquely, has a unique expression. Right? There's not multiple ways of doing that. Okay. Remember that was the property that was equivalent to linear independence. Okay. Okay. So what's good about that is that you can create coordinate systems for abstract vector spaces. Okay, so what you do is you say, well, suppose you have, suppose V is, say V is a vector space, and you have a basis B1 to Bn, a basis of that vector space V. Okay. This is a fancy looking B, in case you don't recognize it. Okay. So you've got a vector space and you've got a basis. Then, like we just said, then for each vector in your vector space, there is a unique expression V equals alpha 1 V1 plus alpha 2 V2 plus alpha n Vn of that vector as a linear combination of the V. Right? That's what we said. We said it before. We just said it a few minutes ago. We're saying it again. Okay. Right. So these alpha i's depend on the V. Right. If you change your V, you change your alpha. You change your alphas. Right. Every V corresponds to a unique set of coefficients. Right. Okay. So we call the vector alpha 1, alpha 2, alpha n the coordinate vector of of V with respect to the B basis. Okay. The coordinate vector of V with respect to, that's what this WRT means, with respect to the basis B. Okay, so let me give you an example. Let's say that V is R3. Okay, and our vector is the one that we normally call 3, 2, 5. 3, 2, 5. Okay. Let me make one sort of obvious comment here. What does this 3, 2, 5 mean? This means that it's 3 of 1, 0, 0, right? 3 of 1, 0, 0 plus 2 of 0, 1, 0 plus 5 of 0, 0, 1. Right? Right? Right. In other words, 3 of E1 plus 2 of E2 plus 5 of E3. Right? Right? You've all seen in the book this notation E1, E2, E3. Right? These E's I use for the standard basis vectors. Right? Okay, so I'm not gonna review that. Okay? Okay, so this 3, 2, 5, really what this 3, 2, 5 is, well actually I should have introduced the notation back here. Yeah, let's call this thing V sub B. Okay, so right, this is the coordinate vector. This thing here is the coordinate vector of V with respect to the B basis. Okay, in other words, it's the coefficients. In other words, it's the coefficients that that you used to make a linear combination of the B basis to get V. Okay. So what this 3, 2, 5 is, if we wanted to write it in our new notation, right? This is the coordinate vector of V with respect to the E basis. Right. If I'm calling, let me call E the vectors E1, E2, E3. Right. But this 3, 2, 5, if you want to be kind of pedantic about it, this is the coordinate vector of V with respect to the standard basis. Okay. Everybody okay? Everybody following? Yes? Mm-hmm. Yes? Okay. You have to be more obvious. Don't just sit there like this. Or I can't read your expressions. You have to please be more exaggerated in your responses. Okay. Okay, so let's get back to the example. So we've got this guy 3, 2, 5. Okay. We've got this 3, 2, 5, and suppose I give you 3 vectors. So let U1 be 1, 1, 1, U2 be 1, 2, 2, and U3 be 2, 3, 4. Okay, so we make this, that turns out to be a basis. Let's call U these 3 guys, U1, U2, U3. Okay, and so I'm going to ask you the following question. What is V with respect to the U basis? What's the coordinate vector of this guy with respect to the U basis? Okay. So take a minute and see if you can figure that out. So think, what are we trying to do? Right? Okay, I'll let you think. think of what you need to figure out and how you would figure that out. What do you need to figure out? Okay, turn to somebody nearby and talk with them. Talk with somebody. Even if it's like, good morning.
I don't have that kind of time. This is like my first night. This is what I've got.
Okay. So what do we need to figure out? What do we need to figure out? We need to figure out what the coordinate vector is. In other words, we need to figure out somebody. Should I'll use my random number generator. Devin.
How to convert from your previous coordinate vector to your new one.
Mm-hmm. Right? So you say, okay, I've got this guy, right? I've got 325, and I want the coefficients that will express it in terms of these guys, right? So you have to figure out what your desire is, right? I want to express, right? I think half of the problem is figuring out what you want, basically, right? Once you know what you want, then it's clear to, then you start making plans of how to get it. But if you don't know what you want, then how do you make plans to get it, right? So you make clear what you want, right? You want to express 325 as a linear combination, of the UIs. Right? In other words, you want your coefficients, A, B, and C, such that 325 is AU1 plus BU2 plus CU3, right? You want A, B, C, right? You want your coordinate vector, right? Okay. So what does this mean in terms of matrices? Say, can anybody express this as a matrix condition? We want 325 as a linear combination of these vectors. Julia.
So you would set it up basically with the goal of trying to reduce it to the echelon form.
Exactly.
So you have just...
Yeah, so you just use these, that's the same thing as using these guys as the columns, right? So 1, 1, 1, 1, 2, 2, 2, 3, 4, times ABC, right? This thing on the right here is exactly this, right? By our key observation that we've used over and over and over and over, okay? Right? It's this, right? Okay, so what does this boil down to? Just to reduce, just a row reduction thing, or find the inverse, right? Find the inverse of this matrix and multiply on both sides by the inverse, right? So what's ABC? ABC you find out by taking the inverse of this, 1, 2, 3, 1, 2, 4, inverse, multiply 325 by it, right? And that'll give you the answer, whatever that is, right? Turns out that ABC is going to be 1, -4, 3. I'm not going to do it, you can do it. Right, so that's the coordinate vector, that's the coordinate vector of V with respect to the U basis. Any questions? Any questions? Okay. Let me give you another one. So just take 10 seconds to do. I don't even know if you need to do this. No, there's no point in this. This is easy. No, I don't need to do it. So here is a basis F, 5, 3, 3, 2, and the vector Z is 10, 7. I want the vector Z with respect to the E basis. So let me put brackets. I think the book's notation is to put brackets around the vector. Like the coordinate, when you say the coordinate vector, you write it like this. I don't know why in my notes it's not like that. Okay. So just think for 5 or 10 seconds and tell me how you would get this. Sherry, how would you get this? How do you get this? What do you do to get it? You should start out by saying you just... Not sure? That's okay. That's okay. Sukhmeet, how about you?
You want to express the in the combination of
these columns.
Yeah.
Right. So what do you do? How do we get it? Right. You say, okay, I want 10, 7 as. So can you express it in matrix form, and then it'll become clear how you figure it out. Right. Say you want this thing as 5, 3, 3, 2 times some coefficients, like C1, C2. Right? And then you would invert this matrix and then multiply on the left side by it, right? And then that would give you your C1, C2. Okay, so this C1, C2 is going to be your vector with respect to the to the F basis. To the F basis. Okay, right. And you can do that. Okay. Jerry.
We have to, I feel like in the past, when we've solved these types of things,
Yeah.
we just reduce them to reduced row echelon form and
Yeah,
use
sure.
that to solve it. Is
Yeah, that's fine.
Is there any advantage to using the inverted matrix way of solving?
I think it's probably faster in this case, right? You've got a 2 by 2.
Yeah.
Right? You just use, the, negative b,
Yeah.
negative b, whatever. Yeah. It's just probably faster. But, it's up to you, right? Right. To calculate the inverse, you have to do a row reduction anyway.
Yeah.
So, it's probably faster to do the row reduction. Other questions? Okay. Okay. Normally I do this lecture in a slightly different order, but let me change the order. Okay. So so that was coordinate systems, right? That was coordinate systems. Now let's talk about changing coordinate systems. Okay. Change of coordinates. Okay, so suppose you have 2 bases, right? So between bases. Okay, change of coordinates between bases. Okay, so suppose we have 2 bases of Rn. Okay. One is called B, and the other is called V. Okay, of course, B is going to be guys that look like this, B1 to Bn, and B is going to be B1 to Bn. Suppose you have some vector, so say B is some vector in Rn, and suppose you know the expression with respect to one basis, with respect to the B basis. Or actually, let me call it X rather than B, so we don't get confused with the basis. So you have some vector X in Rn. You know its expression, you know its coordinate vector with respect to the B basis, right? What's the expression with respect to the B basis? Or really, like, how do we get, can we get this thing from it? Can we get this guy? Can we get the coordinate vector with respect to B from the coordinate vector with respect to B? And maybe some of you are starting to see that already over here. No, over here, right? Maybe some of you see the answer already from over here. Okay, right. So let me make one observation, and then maybe it will become completely clear. This thing on the left, I can rewrite as 1, 0, 0, 0, 1, 0, 0, 0, 1. Right? The vector over here, really this is 3 of 1, 0, 0, plus 2 of 0, 1, 0, plus 5 of 0, 0, 1. Okay. Right? Okay. Anybody saying, what's the relation between the coordinate vector with respect to one basis and the coordinate vector with respect to the other basis? This is the coordinate vector with respect to the standard basis. This is the coordinate vector with respect to the U basis. What's the relation? How do you get from one to the other? Dan?
Elementary row functions.
Could. Right, you could say, okay, let's reduce, but maybe more simple, you'd say, I'm going to invert this guy and multiply on the left by it. Right? Then that gives me a way of getting, right, multiplying on the left by this inverse function, by this inverse matrix, gives me the coordinate vector over there. Right? Okay, let me see if I can make this more clear. Can we get, so you say, well, think. Okay. So this vector x is really, one way of writing it is that it is the coordinate vector with respect to b times the matrix that consists of, whose columns are the basis elements of B. Right? What's X, right? X is right? The coordinate vector with respect to B gives you the coefficients you need to combine these columns to get X, right? So X is this, right? Right? But x is also the coordinate vector with respect to v times this times this matrix, right? Right? Because these are coefficients needed to make a linear combination of the VI that equals X. Is anybody confused by that? I feel like, I have no sense of your understanding. I actually don't have psychic powers. Anybody, is this making, anybody confused by this? Okay. Close your eyes for a second. Close your eyes for a second. Close your eyes for a second. Okay, raise a finger if you're confused. Wait. Okay. Okay, everybody open your eyes. Okay, for the most part, people are okay. Okay, so remember what the coordinate vector is. Okay, right? What's the coordinate vector? What's this? What is that? This thing, remember how you get it? You take x, you express x as a linear combination of the BIs. Right? You express x as a linear combination of the BIs, and then this thing is just those coefficients. Right? This thing is those coefficients. Right? So, what's x? X is this times C1 through Cn, right? In other words, it's this thing, this thing times the coordinate vector with respect to v. Okay. Right? This thing is this thing, right? I'm just substituting it in. Right? What we were doing back here, remember, was figuring out, right, how to get 325. Right? We were figuring out how to get 325 as a linear combination of these columns, right? These, right? And so what we saw that 325 was 1 of this guy minus 4 of this guy plus 3 of this guy. Oops. 3 of this guy. Okay. In other words, 1, 1, 2, 1, 2, 4 times 1, negative 4, 3. Okay, let's go on. Okay, so remember what we're talking about. We're trying to talk about like how to get from one coordinate vector to the other coordinate vector, right? And so you say, okay, this coordinate vector times the V matrix equals this coordinate vector times the V matrix. Right? And so if we want to get from B to V, right, we have to multiply by the inverse, right? So V1 the Vn times V1, the Vn, oops, that should be inverse, times this, times the coordinate vector here, gives us the coordinate vector with respect to the other bases. Okay, so this is how to get from one basis to the other. Okay, and this thing here is called the change of basis matrix. Change of basis matrix from B to B. Okay. You have the coordinate vector with respect to one basis, and it gives you the coordinate vector with respect to another basis.
What do you think of that? It's just like the ratio between the two bases. It's like one times the inverse of the other.
Huh.
Like if your basis was only one vector, wouldn't it just be like
Yes.
the ratio between
Yeah,
those?
that's sort of a cool way of thinking about it. Yeah. 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 Okay. Let's do an example to make this concrete. So, so let's say that one basis in R2 is 5, 2, 7, 3. We have another basis, B prime, which is 3, 2, 1, 1. So write down the change of basis, matrix from B to B prime, say. Okay, turn to somebody nearby and say, here's how you would do it.
Yeah, just that one.
And then you make those two matrix.
Okay, so let me just run through it. So even if you forget how to do it, it's easy to remember, right? You say it's easy to reconstruct. Okay, you say, well, look, I want to get from the coordinate vector with respect to B to the coordinate vector with respect to B prime, right? This is what I want, right? How do I get from here to here? You say, well, you know that the coordinate vector with respect to B times 5273 equals the coordinate vector with respect to B prime times 3211, right? That's by definition, right? This is V. This is V, right? V is the linear combination that you get when you take these coefficients and use these vectors, right? V is the same thing over here, right? So both of these guys are V, right? Both of these guys are V, right? So both of these guys are V, and so to get from here to there, you just multiply on the left by this inverse, right? So you see that, right? To get from, right, the change of basis matrix from B to B prime is going to be this inverse times 5723, right? So the change of basis matrix from B to B prime, right? And if I wanted to go the opposite direction, from B prime to B, well, I'd multiply on the left by this guy inverse, right? So I would get 3121 times 5723 inverse, right? Whatever that is. Okay. And you see by inspection that these guys are actually inverses of each other, right? Which makes sense, of course. Right? These matrices are inverses. The matrix that takes you from this coordinate system to that is the inverse of the matrix that takes you from that coordinate system to this. Everybody all right? Everybody all right? Good. Thank you for nodding. In an exaggerated manner. Some people are very good at reading others' expressions, but I am terrible. My brother says that I myself don't have like normal expressions. Right. So you probably played the game Mafia, right? Mafia, right? Okay. So like. All the time in Mafia, people misread my expression. They're like, oh yeah, he's definitely the Mafia. Look at the way he's like smiling. And I wasn't really smiling. Maybe I was angry or something, right? Or this and that. So yeah, fortunately, if my brother is playing the game, then he'll sort of explain to other people, he can't, he doesn't have the normal expressions. Don't read him like that. I don't think he's Mafia because he's not actually smiling. He's not actually frowning.
Are you at poker because of that? Great poker face?
I don't play poker, but just completely inappropriate expressions. Yeah, I once tried to like take a series of pictures of myself with different like angry, sad, this and that. They all look the same, actually. Just like as something that would be useful to other people. Yeah.
Where are those pictures?
There's somewhere in the cloud somewhere. Yeah. Yeah. And to tell sort of a funny story. So in 2009, I was on sabbatical for 1 semester, which means that I wasn't teaching for like 7 or 8 months, right? And so my normal self, is even less expressive than my sort of stage teacher self, right? My stage persona, right? So during those 7 or 8 months, I used even fewer expressions than now. And so, but when I at the end of the summer, I was like, oh my God, I have to start like showing expressions on my face again. And so, like, a biology professor suggested that I get some masks, like Greek masks of comedy, tragedy, to indicate what expression I was actually feeling on the inside. I thought that was a good idea, but I didn't do it. Anyway, this is just what I just mean to say is that please be sort of exaggerating and expressive in your responses. Okay, so now maybe we'll do the example that I normally do at the beginning of why we might want to change coordinates at all. So we're going to do an example of something called Markov chains. So this is to model a system. Okay, so you've got the system where there's a city and there's a suburb. Okay. And in this system, initially 30% are in the city of the total population, are in the city, right? And they have this behavior that every year 6% of the city population leaves, and 2% of the suburban population leave to the city. Right? These guys go. 6% of the city goes to the suburbs. 2% of the suburbs comes to the city. Okay. And so the question is, how do we figure out? Now, the question is, what happens in the long run? And so we create the following model. What we do is we say, we create something called a state vector. State vector V, which is going to be, this first entry indicates the percentage in the city, and the second indicates the percent in the suburbs. Okay. And of course, the second is going to be 1 minus the first. Okay. And our initial state vector, so initial state vector is of course going to be 0.7, 0.3. No, 0.3, 0.7, excuse me. 0.3, 0.7. Right, because that's what was given to us. 30% are in the city. Okay. And we create a matrix, 0.94, 0.02, 0.06, 0.98, and call this thing the transition matrix. And you notice that if I take this matrix and multiply it by the state vector, right, I end up with 0.94C plus 0.02S, 0.06C plus 0.98S. Right? So you see the purpose of creating this transition matrix. Like it says that if you have, if you have a state CS, you hit it with this thing, the next state is 0.94C plus 0.02S, 0.06C plus 0.98S. In other words, it's saying what happens according to the description, right? 0.94 of the city population stays, and we gain 0.02 of the suburban population, 0.06, and 0.98 of the suburban population stays, and you gain 0.06 of the city population, right? So this is the new state, right? This is the new C. This is the new S. Okay, and so this is what this is the state after 1 year. Right? And so it's this way that you can create this sort of discrete system that models the behavior of your city. Right? So every year you just apply A one more time. Right? And so our question is, what is our question translates to what is the limit of a to the n times 0.3, 0.7 as n goes to infinity. Right? We want to know what happens in the long run. In other words, as time heads off towards infinity. It turns out that the limit is 0.25, 0.75 as time goes to infinity. Okay, as time goes on, so you can figure this out numerically, but we'll see how to do it in a different way in a second. 2 minutes, so let me sort of speed this up. Okay. This vector here, so let me ask you, what if I apply A to this vector? What if I apply A to this vector, this limit vector? That's like adding on one more year, right? What's going to happen? Nothing, right? Because you're really taking the limit as n goes to infinity, right? And you get this thing. You're adding on one more n. That's like saying a n plus 1. Well, you're still going to get the same thing, right? So nothing happens, right? Nothing happens. It's fixed, right? It's what's called a steady state vector. Okay, so this can be clarified using a different basis. Okay, so so here's what we do. Magically, we choose U1 to be 1, 3, and U2 to be negative 1, 1. Okay. 1, 3 is 4 times 0.25, 0.75, the vector that doesn't change. So A times 1, 3 is just 1, 3. And it's a multiple of the steady state vector, so it doesn't change either. Okay. A times U2, if you calculate it, turns out to be a number times U2. U1 and U2 are what are called eigenvectors. And we'll see them, we'll do a lot with them later. Okay. Now, if we write 0.3, 0.7 in terms of U1 and U2, right, as a linear combination of the U1 and U2, we see that 0.3, 0.7 actually turns out to be 0.25 of U1 minus 0.05 of U2. Okay. And then the result becomes clear. If we look at the limit of a to the n, times 0.25 U1 minus 0.05 U2, what happens? What happens? Well, every time you apply a to this first part, what happens? A times 0.25 times U1. Well, U1 doesn't change when hit by A, right? So what happens to that first part is nothing, right? And then what happens to the second part? As you apply A to U2, every time you do it, what happens? It gets shrunk, right? By some percentage, right? It gets multiplied by 0.92, right? So it shrinks by 0.92 every time. And so as time goes onwards, it goes to 0. And so you end up with this. In other words, 0.25, 0.75. So the point of this example is that sometimes changing the basis makes things simpler to understand. Okay, the behavior of the transition matrix, right? The behavior of the transition matrix is sort of complicated. But if you think of it in terms of U1 and U2, it's very simple. Okay, so it's that's the point. Sometimes if you change your basis, then phenomena become easier to understand. And we'll see a lot of this later on. Okay. Sorry to keep you over.